been a day, my hair is a mess, whatever. Back home, use my own whiteboard, we'll get it figured out. So our next unit is going to be looking at electrodynamics. Electro referring to electrical stuff, dynamics looking at the changing stuff. So dynamics as a fundamental thing is going to involve a lot of forces. So when we talk about electrodynamics, what we're really saying is we're going to look at the forces surrounding things like electricity, charges, things like that. This will have a pretty significant application in circuits, how electricity works in general, as well as things like magnetism, which is heavily involved in motors and generators, which run our daily lives. So to get started, let's just look at what we're really talking about here. I'm going to use red. Don't mind me breaking my own garbage. Okay. Red is positive, make blue negative. What I've drawn here is two charges. We're going to say each of these has a specific amount of charge. We're going to say it is equivalent to 1 coulomb of charge. 1 coulomb. Charges are measured in coulombs. Any idea why they're named coulombs? Coulomb is the guy who figured this out. So, 1 coulomb of charge is actually a massive amount of charge. What do I mean when I say charge? Have you ever, in drier months, like winter, rubbed your feet on the carpet and then touched someone and had that quick zap? That is charge. That is you building up a certain amount of charge and then releasing that charge. So charge is a buildup of electrical, it's like energy. It can be kind of a challenging concept to wrap your head around at first, but it will make sense because of how much we interact with it on a regular basis. Charge is to electrodynamics what mass was to all of our kinematics and regular dynamics. So when we look at charge, we need to keep in mind that we can have positive or negative charge. This is going to be a newer concept because when we work with mass, we weren't able to have negative mass. That's impossible. It's a contradiction. We can't even wrap our heads around what it would be like to have a negative mass. But we can very easily have negative charge. A way to think about this is this could be a bundle of electrons, and this could be a bundle of protons. If you recall in atomic structure, atoms are made of protons, neutrons, and electrons. Protons have a positive 1 charge, electrons have a minus 1 charge. So just off the bat, that's what we're looking at. So 1 coulomb of a positive charge and 1 coulomb of a negative charge. What's going to happen? What's going to be the force around these things? I imagine at some point in your life you've played with magnets, you've seen that these things can pull and push each other apart. Well, electrodynamics is the fundamental force that drives magnetism in a rather interesting way that's not immediately apparent. But what we can have is something like I can take a glass rod, I can rub it with some fur or hair or something. Traditionally, it's people use cat hair for the demonstration. I don't know why. But then if you try to touch a balloon or something light with it, it'll push it away or pull it towards it. Things like that. So what's happening in those situations is we build up a difference in charge. So differences in charges will cause a force just like masses will cause an attractive force. The difference here is because we can have this positive or negative, we're going to have two different options. We could have a pull or a push. Okay. So when would we have a pull? Well, we'd have a pull in a situation like this, where we have opposite charges. These would want to come together. So opposite charges attract. Okay. If I had the opposite situation, where I had two positive charges, well then I'd have the same type of charge and they would actually push away from each other. So same charges repel. So if I put little vectors on these guys, then these guys are both going to have a force pulling them towards each other. Remember Newton's third law, that force is going to be equal and opposite. So force 1 here, F1 versus F2, F1 will equal F2. They'll be equal in how much they're pulling towards each other. In the same way, down here, our forces, because they're the same type of charge, they're going to repel. So my vector will look like that. And how much are they going to repel? Well, that's going to be, let's say this is F3, this is F4. Well, F3 will equal F4. Now, the only difference in these forces will be the direction, because we're saying all of these charges have 1 coulomb of charge. This one is positive, this one is negative, these two are both positive. So all of these forces will be the same magnitude. The only difference will be that they will either pull together or push apart. Okay, so that's going to be a thing that we'll need to keep an eye on. All right. So the next thing we want to understand is, how do we figure out the magnitude of these forces? How much is that force going to be? Well, that's actually not too difficult to figure out. In order to figure that out, we're going to have a little equation called Coulombs Law. And this is going to look very similar, not just like, but very similar to Newton's law of gravitation. And it's going to have very similar qualities. So we're going to say force of electrostatics is equal to, and we're going to use K, that's going to be our constant. And then we're going to use Q1 and Q2 over R squared. Now let's go over these variables. F, obviously, that's a force. So F is our force, measured in newtons. K, this is Coulomb's constant. And it is equal to 9 times e to the 9th. This is a very large number. So where in gravitation, that gravitational constant was a very small number, I think I've got it right here, 6.67 e to the negative 11, the Coulomb constant is 9 times e to the 9th. That is 9 billion, okay? So then we've got Q. Both Q's will represent the same thing as a variable. Q is going to represent our charge. And this is going to be measured in coulombs, the capital C. So Coulomb, capital C denotes a coulomb. Now, like I said before, a coulomb is a massive amount of charge on its own. One lightning bolt has about 15 coulombs of charge. So when we use a full coulomb in a problem, it's mostly going to be for the convenience of calculations. But in real life, we're more likely going to be using much smaller values. So then R, that's going to be the distance between centers. Okay, so that R value, that is really talking about the distance between these centers. So it's not the forces from the edge to the edge, it is from the middle of that charge to the middle of the other charge. That is my R value. Okay? Good. So let's say, for the sake of this problem, that R is equal to 1 meter. Then I can do my calculations to figure out what is this force. Well, very simply, that would be F equals K, which is 9E9, times Q1 and Q2, 1 and 1. So this is going to be times 1 times 1 divided by then 1 squared. 1 squared is 1, cancels out, cancels out, cancels out. So my force here, with a full charge of 1 coulomb, that is 1 meter apart, is going to be 9 to 3,000 million billion newtons. That is a massive amount of force. So 1 Coulomb is a very large amount for that very reason. Okay, so what else do we need to keep in mind? Well, first off, it's going to be a little iffy looking at these charges and positives versus negatives. We want to be careful in our calculations, because if I just put in, if I say, okay, well this is a positive one and this is a negative one, so a positive one and a negative one, well there's only one negative in here, so this whole thing is going to turn out to be negative, right? Well, so then my force must be negative here. But that's not necessarily true. Remember, in either case, my two forces are going to be going in the opposite directions. So one's going to be negative, one's going to be positive, and it's not going to be based on those negative numbers. So I need to keep that in mind. I'm not putting a negative charge into my equation. I'm using the fact that one is positive and one is negative to determine what direction is that force going to go. Towards the other source of charge or away from the other source of charge. That's going to be a thing I have to do mentally. It isn't just going to show up in the math. So a way you can keep that in mind is it's going to be the absolute value of these two together. So multiply these together, just the absolute values. Keep the positives and negatives out of it. Don't worry about the integers. Then, once you have the magnitude of your force, figure out the direction based on positive and negative. All right? Let's look at this on something that doesn't just use a bunch of ones. Okay. So, since this looks so very similar to Newton's universal gravitation equation, let's use that as our example. So I'm going to leave this up for now. So force of gravity, which is always going to be an attractive force. You're not going to see a repulsion due to gravity. It's going to be G times M over R squared. Now, when we have things like a planet, the mass is so large that this force really dominates. On top of that, for something about the size of a planet, the charge is pretty much going to amount to zero. We're basically going to have a zero net charge for a planet. So the electrostatic force is insignificant. On our level, the force that keeps us pushed down to the ground, that's going to be the force of gravity. That is pretty significant in our lives. But the question comes up, well, why don't I just fall through the floor? I mean, if I've studied chemistry, I know that there's all this space between atoms. Why don't my atoms just slip in between the atoms of the floor? Well, that's because as the atoms get closer and closer and closer, they all have electron clouds that are opposite charges, or I'm sorry, the same charges. So they are repelling each other. So as they get closer and closer and closer, this force gets bigger and bigger and bigger. And so, therefore, the floor is pushing back up on me because the atoms, the little electrons in the atoms, just these little electrons, are pushing away from each other. That's why. That's it. Nice and simple. It's such an, I just find this so interesting. So let's look at the subatomic level. So on our level, these two forces are really kind of balancing each other out. We're really dealing with both of them. I mean, this is the force that drives things like electric motors. I mean, the starter in your car is a little electric motor that's running because of this. So on the subatomic level, gravity becomes so insignificant that it doesn't even matter. Even between lead and helium, which have massively different numbers of particles, their masses are still so small that it's insignificant. What's really driving things on the atomic level is going to be that electrostatic force. So let's look at a couple just elementary particles, which would be a proton and a neutron. Let's look at the forces between them. Okay. Let's actually look at two protons. That'll make things a little easier. If I look at a proton and an electron, I have to deal with the mass of an electron, which is insignificant, but protons are going to have the same mass. So let's go proton, proton. Let's put them at 0.3 meters apart. Just arbitrary. apart. And what is their charge going to be? Well, this is a good question. The charge on an electron and a proton are equal but opposite, and it is the smallest charge you can get. It's known as the fundamental charge. We are unable to have a charge less than this number, and so because it is so important, we will denote it with a little special letter E. The fundamental charge of a proton or an electron is, let's see if I got this right, it's 1.60 e to the negative 19. Not only can we not have a charge smaller than this, our charges will go in increments of that value. So it would be impossible for me to have a charge of 1.70 e negative 19 because I can only add another 1.6. I can double this and keep adding on 1.6 e to the negative 19, but I can't get in between that. That might be a little more confusing than it needs to be. If it is, ignore it. Okay, so 1.6 e to the negative 19. That's going to be our charge here. Now, what is the mass of a proton? That is also extremely small. A proton has a mass of 1.67 e to the negative 27. Now, you can already tell which one is going to be stronger here, but let's go ahead and do the math anyway. So, I've got two protons 0.3 meters apart. I've got a charge, I've got a mass. So first, let's do our Coulombs Law calculation. So the force, the electrostatic, is going to be that K value, which remember is K equals 9.9E9. There we go. The gravitational constant, if you remember, is 6.67 e to the negative 11. 6.67 e negative 11. Great. So, electrostatic force, K times charge number 1, 1.6 e negative 19 times 1.6 e negative 19 divided by 0.3 squared. Okay, let's plug that into our calculators. Okay, punching all these numbers into my calculator is 2.56 e to the negative 27. Now, the force of gravity on this same situation, we're going to have our universal gravitational constant, and then 1.67 e to the negative 27 times the same value, all divided by 0.3 squared. Alright, and punching that into our calculators, we get 2.07 e to the negative 63. So while both of these numbers are extremely small, this one is extremely much smaller. So, go ahead and start on the worksheet. Start making those calculations using Coulombs Law. Keeping in mind, like charges repel, opposite charges attract.